In this video, I want to discuss the NFA-to-DFA algorithm. That is, how you remove nondeterminism from a machine. We can see this machine is nondeterministic both by the lambdas that you see on these transitions and by the fact that there's two ways to go on B out of state 1 and there are two ways to go on A out of state 1. Alright, so step 1 in this algorithm is to make yourself a table of transitions representing this non-deterministic machine. Your table will have a row for every state, so we have states 0 through 6 in that table, and the table will have a column for every character of your alphabet. And for us in this machine, that is A and B. Sorry about the crookedness of my table. Now, when you're making this table, you look for transitions that leave the state directly labeled with this letter. So when we're doing 0, we're looking at 0 to see if there are any transitions labeled A that leave directly out of state 0, and there are not. I usually just put a little dash for that, and there's also not any leaving out of 0 that say B. Now let's do state 1. There are 2 transitions out of 1. 1 goes to 5 and 1 goes to 3 for the letter A. And so we put both of those in this table. This is a table whose contents are sets of states. And so we have 3 and 5. And I normally put them in numerical order just to make sure that I'm consistent in how I write things here. Now looking out of state 1 for the letter B, I see I have a transition there and I have a transition there. Now, here's something interesting about this algorithm. When you have used the character that you're wondering about, in this case B, and you have landed in a particular state from which there are lambda transitions, then you incorporate the states you can get to using those lambdas into the group of states you go to. But first you have to use the B. So when you're in state 1 and you use the B to come back to here, you see, well, there's a transition over to 6. So I will pick up not only 1, but also 6 from that transition right there. But then there's this transition too. There are no lambdas out of here. So we're going to get 1, 2, and 6 as the contents of the table here. Now let's do state 2 on A. State 2 on A takes us to state 1. Remember that if you land somewhere where there are lambdas available, you take those lambdas too, after you've used the letter. So we pick up 1 and 6 here. State 2 on B, don't go anywhere. State 3, down here. On the letter A, nowhere. On the letter B, you go to 4, and there are no lambdas out of 4, so that's all you get, just 4. State 4 on A, you go to 1, and there are lambdas available, so you pick up 6. 1 and 6. 4 on B, nowhere. 5 on A, nowhere. On B, you go to 1. And then you can slide over to 6. So you can be in 1, you could be in 6 if you wanted. State 6, no edges out. So no A, no B. That is your table for the non-deterministic machine. Now, very critical step. You have to get your start state right for your deterministic machine. It will be the original start state, 0, together with any states you can get to from that original start state using nothing but lambdas. In our case, we could be at 1 using nothing but lambdas. We could be at 6 using nothing but lambdas from 0. So our start state for the deterministic machine is going to be 0, 1, 6. We begin our table. We'll have A, we'll have B. And now we just look at this table and we union together contents of rows. So we are looking at rows 0, 1, and 6 in the column labeled A. 0 gives us nothing. 1 gives us 3 and 5. 6 gives us nothing. Put all that together and you get 3, 5. Look at row 0, row 1, row 6 under B, and you get 1, 2, 6. Now, these two groupings, 3 and 5, 1, 2, 6, become rows in this table. Here's 3, 5. Here's 1, 2, 6. And we keep this process up until we don't turn up anything else new. 3 and 5 under A gives us nothing. That tells us there's going to be a trap state in our deterministic machine. 3 and 5 under B gives us this 4. Together with that 1 and 6, I put them in numerical order and I get 1, 4, 6. That's a combination I haven't seen yet, so I put it into my table. 1, 4, 6. Now, 1, 2, and 6 under A. 1 gives me 3, 5. 2 gives me 1, 6. And 6 gives me nothing. So I have 1, 3, 5, 6. For B, under 1, 2, and 6, all I get is that 1, 2, 6. Now 1, 2, 6 I've seen before, but 1, 3, 5, 6 I have not. So I add 1, 3, 5, 6 to my table. Now let's do row 1, 4, 6. We get 3, 5, 1, 6, and nothing. So that's 1, 3, 5, 6. And we've seen that before. 1, 4, and 6 for B just gives me 1, 2, 6. So I don't get anything new from that row. Now let's do 1, 3, 5, 6. 1 gives me 3 and 5. 3 gives me nothing. And 5 and 6 gives me nothing. So all I get is a 3, 5. And I have seen 3, 5 before. 1, 3, 5, 6 for B gives me 1, 2, 6, and 4. And 1, 6, and nothing. So the 1 and 6 here don't add anything new. I have 1, 2, 4, and 6. 1, 2, 4, and 6. Alright, that's new. So I add a new row. 1, 2, 4, 6. And now I look up stuff for that. 1 and 2, and 4, and 6. So I'm going to get 1, 3, 5, 6. Here. And 1, 2, 4, 6. All I get is 1, 2, 6 over here. Alright. Now both of those I've seen before. I didn't leave out anything, did I? Sometimes I'll forget to add a row for something that I should have added a row for, but I don't think I did in this case. Okay, so now let me erase this little bit of the machine or the table that I have there, and I'm going to try to draw this machine. I'm just worried about running out of room in my picture here, but I think I can scroll some. Alright, so down I go. Now, this is my start state, so I'll begin over here. I usually start at the left with a state named 0, 1, 6, and I'm not going to worry with the commas. 0, 1, 6 on A takes me to 3, 5. On B takes me to 1, 2, 6. 3, 5 on A doesn't take me anywhere. Now if I want, I can put in the trap state and go there. At the moment I don't want to do that because my machine's going to be crowded anyway. On B I go to 1, 4, 6. Now state 3, 5 is finished. How about 1, 2, 6? On A I go to 1, 3, 5, 6, and on B I come back here. So let me do the B. Here's the B coming right back there. And on A, I go to 1, 3, 5, 6. All right, now let's do state 146. On A goes to 1356. On B goes to 126. Getting a little messy here. All right, 1356 on A, oh dear, goes to 35. So there on A. And on B goes to 1246. 1, 2, 4, 6. And from that state, on A goes to 1356, back over here. And on B goes to 126, over there. Now, which states are accept states? Go back to your original picture. What was your accept state over there? State 6. Any state that's got a 6 in its name is going to be an accept state. So this state at the very beginning is an accept state. So is 126. So is 1356. And 146. And 1246. Those are all accept states. This one is not, and the trap is not. Now, oops, I didn't mean to do that. Got too close. What I want to do now is run the minimization algorithm on this machine. So I'm going to copy this machine. And make a new picture. Just in case I need that back, I'm going to save that. And paste my machine over here. Alright, now these names are really not very pleasant for my next step. I want to run that minimization algorithm. So I'm going to erase these names. And I'm going to just give them names that are one character. I could use capital letters. I could use different numbers. I could use whatever I want. I just want better names. How about I'll use capital letters? I'm going to call this P. I'm going to label all my accept states first. Q, R, S, T. Now I'm going to put that trap in up here. I'm going to call this one U, and I don't want to do V because my writing is too messy. They'll look like U, so I'm going to call that W for the trap. Alright, so now minimization is the process of putting all your states into one container first and then dividing up, partitioning that set of states down into smaller and smaller subsets until you get all the way down to states that are serving the same purpose and can be combined. So the very first thing we do is make a set of accept states, which would be P, Q, R, S, T, and a set of non-accept states, U and W. That's our first partitioning. And now we begin breaking the sets down into even smaller sets. So let's pull state P down and then examine state Q with P to see if they need to stay in the same set or if they need to split up and go to different sets. So we look at Q and we look at P in the picture. And we say, where do they each go on the letter A? And then where do they each go on the letter B? If they go to the same set on the previous row on both letters, then they get to stay together for now. But if they go to different sets on the previous row on the same letter, then they have to split up. Let me show you what I mean. We're looking at P and we're looking at Q. On the letter A, P has a row to U. Q has a row to S. So you're looking to see if U and S were in the same set on the previous row, and they were not, because U is a non-accept state and S is an accept state. So these guys have to split up. So I start a new set for Q. Now what about R? Can R be with P? Can R be with Q? Does R have to go by itself? Let's see if R can be with P. Look at these two. Where do they go on A? P goes to U, R goes to S. U and S are not together on the previous row. So R cannot be with P. Can R be with Q? Look at Q, look at R. On the letter A, R goes to S and Q goes to S. They go to the same place. If they go to the same place, then they certainly pass the test because that place was with itself on the previous row. On the letter B, they go to the same place. So Q and R are going to stay together for the duration of this algorithm since they go to the same places on both letters. Now, S and P. Here's S, there's P. On the letter A, P goes to U, S goes to U. On the letter B, P goes to R, S goes to T. Were R and T together on the previous row? Yes, they were. So S can, what was I testing? I can't even remember if I was testing S with P or S with R. I was testing S with P. Yes. So S can be with P. All right, what about T? T with, let's test it. I can pick either P or S to see if T can be with this group. I generally pick the one closest to it in the picture. I didn't mean to make that scratch mark right across my picture here. Sorry, I'm not the world's greatest video maker. I have no idea what that was. All right. Now I'm testing T with S. On the letter A, T goes to S, S goes to U. Well, T and U were not together on the previous row, so T cannot be with S. That means that this set closes. What about T with R? T and R. On the letter A, they go to the same place. They both go to S. On the letter B, they both go to the same place. T goes to R, and R goes back to R. So T can be with these guys. Now what about U and W? On the letter, whoops, this should have been an A right there. On the letter A, they each go the same place. On the letter B, U goes to Q, but W goes to itself, and those guys were not together. So U and W are going to have to split up. Now we keep going because this row changed after that row. We got to get two rows that are exactly alike before we can stop. So now we go again. And now when we say on the previous row, we mean this row. So can P and S stay together? Here's P, here's S. On the letter A, they both go to U. On the letter B, they go to R and T. Were R and T together on this row? Yes, they were. So P and S can stay together. Now, what about Q, R, and T? Let's try R with Q. R with Q. Here's Q up here. And I remember they both go to the same place on both letters. They both go to S on A and they both go to R on B, so they can stay together. And the same thing's going to happen with T, isn't it? If I'm remembering right. T and R both go to S on A, both go to R on B, so these guys get to stay together. And these other two are already separated, so this row looks exactly like the last row, and we can stop. Now we draw the new picture. Here's our new picture. The start state used to be P, now P is with S, so my start state's going to be called PS. From the original picture, on the letter A, P went to U, so PS is going to go to wherever U is, U's by itself. So on A, PS goes to U. And P on B went to R. R is now with Q and T. So here's a state called QRT, and B goes there. U on A went to the trap. I'm going to leave that invisible since my picture's crowded. On B went to Q, and Q's down here now. So I'm going to make it go down here. Pick one of these from your original picture. Let's pick Q and say, where did it go on A? It went to S. Where's S? Oh, S is over here now. So that's where we go on A. What about Q on B? Q on B went to R. Well, where's R? R is here. So it just stays right here on B. And that's the end of our picture. Everybody's somewhere. Now, which states become accept states? Whatever they were up here, they stay that way. So P was an accept state. That means that it'll be an accept state still with S. And we know S was because we started out just putting them in the same place. And Q, R, T, they were accept states. U was not. So now that is our minimized machine. And that is doing the same job as that regular expression, as that non-deterministic machine we started with was doing. Hope that helps.